So Houdini H17 is out, and it brings a wealth of cool new stuff. And to me, one of the most exciting features is Vellum, a new unified solver for all kinds of soft body dynamics. That means wires, hairs, cloth, soft bodies like balloons, and all kinds of squishy things. And what makes Vellum special is that it's fast and it's relatively stable. So how does it work? When you look at it from afar, Vellum is, air quotes, just an expansion of grains in a sense. So grains in Houdini under the hood was a technique called PBD, position-based dynamics, a very fast method to solve dynamic systems coming from the world of real-time and games. And what makes PBD so effective is, amongst other things, the way it handles constraints and collisions. So imagine we have this virtual string here, composed of those points here, which in essence are spheres because they have a radius for collisions, so those tiny spheres, and in between them those constraints. So everything PBD does is approximate a given geometry with a system of points, or spheres that is, and a set of constraints, in this case just linear constraints. So these constraints between those points may have a given stretch. And what we do next is we just try and pull one of those points downward, like this. And this is the first step when we pull this string. And it really doesn't look like what you'd expect from a string that is pulled downward, because what you'd expect is more like this shape here, like a triangle connecting those points in a line and those points in a line. So instead of trying to solve the whole system of springs and points that makes up our virtual string here, what position-based dynamics does is it enforces the constraints iteratively, sphere by sphere or point by point. So let's assume we start from this point here, and next we try to relax the adjacent point to a position where both constraints are met, so where this distance here between those points is minimized, which would be this position here. Let's do the same thing here for this point, and for this point, and for this point, and finally for this point. So after we've run through all of those points once, we have a solution for the string that is a bit better, but it clearly doesn't look like what we'd expect yet, because this is clearly not a linear connection or not the shortest path between those points and those endpoints here where the string is fixed. So let's run through all these points again, and we arrive at this configuration here. And let's again run over all these points one more time, and we finally arrive at this configuration here, which finally looks somewhat plausible. So the important thing to notice about PBDs is that as a dynamic system, it tries to relax constraints and collisions bit by bit. That means point by point or constraint by constraint. And only with high enough iteration counts, this will yield plausible results. So the constraint iterations and substeps are one of the major factors in PBD systems. But all of this was feasible with grains before Houdini 17. So what makes Vellum so special? Well, amongst other things like an easier workflow and more stable solvers, it's these guys here, constraint types. So what Houdini 17 now offers are additional constraint types for our simulations, which are in essence 3 constraint types and a combination of them. On the one hand, it's our old school distance or length or stretch constraint here. So those points here, connected by those 2 constraints, should remain a given distance apart. And those constraints can have a stiffness and a damping, so you could think of them as linear springs. However, with Vellum, we get additional constraint types, such as the rotational or bend constraints, that keep the angle between primitives or the angle between constraints. For example, when you have a wire, it can only bend so far. You could think of this as kind of a rotational spring, keeping the angle between those 2 primitives here. And finally, we have volume constraints that try to preserve the volume of a geometry. So this only works if you have some piece of geometry that actually has some volume to it. For example, here, this tetrahedron, where we tell the solver to keep this volume of this whole geometry here. And all of the other constraints that are available in Vellum are a combination of these 3 basic types. And I hope I didn't forget anything here, but I think it should be these basic 3 types. So let's look at how to set up a Vellum solver and a Vellum simulation. So after firing up Houdini and dropping down a GeoSop, diving in there, you will notice, happily, there is no file to delete anymore. So now about 50% of your work time have been saved. In order to have a look at Vellum, let's start out with our pighead test geo. Just set its difficulty to easy, like this. And then let's have a look at the Vellum set. So when hitting tab and going to the Vellum submenu, you can see there's quite a bunch in here, with the Vellum solver being the node that solves our system. And as you can see by now, SideFX decided to do something different this time with Vellum. Yes, on the one hand, the DOPS nodes for Vellum are there, but one of the major use cases, I think, will be in SOPs only. And I think SideFX reacted to most of the artists being most comfortable in SOPs, with implementing a SOP wrapper for the whole Vellum toolset as well, which comes with these new nodes here, having those 3 inputs. The first input being the geometry that's used for simulation, the second one being the constraints on this geometry, and the third one, collision geometry. So how do you set up this geo? You use Vellum constraints to configure the behavior of your geometry. So let's drop down a Vellum constraint here and wire this into the solver. The simulation geometry goes in the first point, and let's drop down a grid, zoom out a bit here, and move this downwards a bit like this, and use this as a collision geometry. So in the Vellum constraints here, we can choose different constraint types. And I mentioned that the basic ones here are the distance along the edges, the bend, in this case across triangles, and the volume, the tetrahedral volume that we've been talking about. However, there are lots more of constraint types, and those are a mixture, a combination of those basic constraints. So for example, hair has a bend, a length, and also a twist constraint, while for example, string only has a bend and a length constraint, but no twisting. Cloth is your basic cloth as you'd expect, with a bend and a length constraint. Tetrahedral volume tries to conserve the volume of tetrahedrons, so you have to feed in tetrahedral meshes. Struts constructs internal struts that connect opposing sides of a mesh, so you end up with kind of a cheap, very easy to simulate soft body. And pressure tries to keep the pressure inside of your mesh constant. So the difference between tetrahedral volume and pressure is that tetrahedral volume is more akin to FEM and more akin to a filled balloon or a filled shape that's filled with liquid, while pressure is filled with compressible fluid, that means air or gas. Also, there are additional helper constraints, for example, pin to target, attached to geometry, to attach a given piece of your simulation geometry to another geometry or to a target, and also stitch points, for example, if you want to stitch together the front and the back side of some cloth to generate some garment. With that, let's just set the constraints to cloth, and let's drop down a null here. And let's have a look at the constraint geometry that Houdini is generating here. So when I zoom in, you can see this is your bread and butter cloth constraints, as you know them from grains too, so those interconnected points from your mesh. Let's highlight the Vellum solver here, zoom out a bit, and hit play to see how this simulates. And you can see, even on my kind of slowish machine, this already yields interactive frame rates. So let's stop this and add to this another constraint. Wire this in between here, and let's set this one to struts and highlight the resulting constraints too. So we can see now, instead of the simple cloth here that's coming in from the first Vellum node here, we added those internal struts connecting opposing faces, opposing sides of your mesh. And this trying to conserve the volume or the shape of the mesh a bit better than a pure cloth. So let's hit play on this too. And you can see simulation times are a bit longer now. However, my geometry wiggles around a bit, behaves a bit like a soft body, but does not collapse, as with the pure cloth constraint as before. Let's set our second constraints to pressure this time. Again, let's highlight this. So a few additional constraints here, but not as many as before. And trying to conserve the internal pressure now. Hit simulate on that too. You can see that too doesn't simulate as quickly, and it's a bit more wobbly, a bit more bendy, allows for a bit more flexibility, without the whole collapsing geometry that came from the pure cloth constraints. So you can see with the combination of a few constraints, you can simulate different behaviors and get your objects to behave very differently. And as a shortcut for those behaviors, Vellum, when you go into the Vellum submenu, has got some presets for those. For example, configure balloon is a combination of a Vellum cloth and a Vellum pressure, as we did here, and Vellum soft body is a combination of cloth and struts, as we configured previously. Also, there is the pure configure cloth, which is just a simple cloth constraint. There is the hair, which is a simple hair constraint. And finally, from those presets, there is the grain. So Vellum comes with all kinds of presets, which makes it really easy for new artists that dive into this technology to set up simulations that are really simple and kind of performant, definitely faster than previous wire solver or FEM. So let's play around a bit with this and modify our collision geometry here by adding a translate SOP, transform that is, and let's on the one hand resize this grid here to be a bit smaller, and then let's move it up on the first frame, so translate it upward like this, keyframe it, move forward to frame 48 or maybe 72, and let's move it down a bit like this, and set a keyframe 2. So now my pressurized pig head should get squished by dropping down a merge here and merging those two grids. So let's see how that looks. And that is working stable, without any protrusions or something. So let's make this animation a bit more aggressive, and on frame 72, move our grid down a bit further. And yes, this updates interactively, which is really, really nice. So let's set the keyframe to -1 and resim this. And still, this is decently stable. I mean, it jiggles around a bit here, and we saw some protrusions, I think, like here in this frames. Oh no, see, that's even just the ear coming out of the other direction, the other side of the grid that's squishing it. However, if at some point, and let's try provoking this by squishing it even further, if at some point, like here, we're getting protrusions or weird simulation artifacts happening here, the main settings to dial in are on the Vellum solver in the constraint iterations and the substeps. I mean, we talked about constraint iterations, and substeps basically lets the simulation run a given amount of time per frame. So the simulation is run 1 time per frame. However, when I increase the substeps to 2, I'm running through this whole simulation twice, and each simulation does half the time step. So the first simulation brings all my points, all my geometry to frame 0.5, and the second substep brings it to 1. Of course, at the cost of longer simulation times. And let's check. Well, there are still some protrusions, which might come from the really coarse mesh that I put in here. So let's subdivide our pig head before we feed it into the simulation and resim this. And we're still getting some protrusions. So again, let's increase the substeps, double it to 4 substeps, and resim the whole thing. And maybe what we could do instead is try dialing down the constraint iterations and have the substeps compensate for that. Let's again check how that worked out. And yeah, that seems to have fixed it. Also, one thing to keep in mind when you're squishing stuff that's really tightly, these tight spaces here, keep in mind that your cloth can have a certain thickness, which in this case is not enabled because we didn't enable it, we built this manually. However, when you're using the Vellum balloon to set up this behavior, in the cloth part of it, we have on the one hand a mass and then a thickness configured there. So you might not want to squish the balloon mesh past its minimal thickness. However, in our case, that's something we can disregard, and we end up with this beauty here. Now, this mesh still looks somewhat coarse, so if we switch off the wireframe, we can see some shading artifacts here. And to get rid of that, Vellum has its own post-process node, which allows not only to smooth out the positions a bit and thus get rid of some artifacts, it also has some post-detanglement, so we're getting rid of intersections, but also we can subdivide the mesh after a simulation and thus generate a higher resolution mesh out of a low-res sim mesh, like this here. Let's hit play, toggle real time. And we get this squishy balloon here. So that is the basic standard easy Vellum workflow. Let's have a look at something a bit more destructive in the next part of this mini-series. And while we're here, I'd like to point out that if you're looking for additional Houdini content, you can head over to our Patreon. We've got in-depth courses there, render files, and lots of more stuff. And I'd like to say a special thank you to all of our patrons for supporting us, especially Kyoko Sakane, Martin Ögren, Joseph Howerton, Nick, Chris Hebert, Rafik Anadol, Rob Bryant Jr., and Mohammed Alabri. Thanks so much, guys.